Okay, let's slowly get started. Other people will join by that time. Well, first of all, we can complete the material balance. That is the same old problem that we have done long, long ago. Material balance kind of problem. We are having 10% conversion, right? That means out of the, this is for ethylene, 10% conversion of ethylene. So out of the 25 gram moles that are going to that are entering, we are taking basis as 100 gram moles of the feed. So if we are taking 100 gram moles as the feed, entering is 25 gram moles, 8 and 67. So when we say 10% conversion, out of the 25, 2.5 gram moles will react, and 2.5 gram moles will react. Let me just zoom it so that properly we can see everything. Yeah. So 2.5 gram moles will react. So 22.5 gram moles will remain unreacted. So 2.5 gram moles of ethylene react. They react through both these reactions, right? Desired as well as undesired. And 85% selectivity. That means out of the 2.5 gram moles that react, 85% of 2.5, let's see how much is that. 85% of 2.5, that means 2.125 gram moles react through the desired reaction, and 2.5 minus 2.125, or 15% of 2.5, that is 0.375 gram moles of ethylene react through the undesired burning reaction. Okay, now if you start looking at material balance for the stoichiometry for the first reaction, 2.125 divided by 2, that is oxygen consumed, will be, for the first reaction, will be 1.0625, and ethylene oxide produced would be 2.125. So straight away we can say that ethylene oxide produced would be 2.125. Nitrogen is going to remain unreacted, 67. Straight away we can write. Now let's balance the second reaction. So C2H4 ethylene burning, I will get 2 of carbon dioxide, I will get 2 of water, and I will require 3 times the moles of oxygen. So 0.375 gram moles of ethylene react to make ethylene oxide. Multiplied by 2, I will have 0.75 gram moles of carbon dioxide getting generated. I will have 0.75 gram moles of water getting generated, and oxygen consumed would be 3 times 0.375. So 1.125. So total oxygen reacted 1.0625 through the first reaction, plus 1.125, 0.375 into 3 is 1.125. So 1.125 plus 1.0625, total amount of oxygen reacted 2.1875 out of this 8. So 8 minus 2 point whatever that number was, this is oxygen remaining is 5.8125. CO2 generated would be 0.75 gram moles. Water generated would be 0.75 gram moles. Like material balance, we have done long ago, and it's almost decade since we have learned material balance. All right. Now, as I was, let's look at the first problem. So we have got material balance. Any issues up to material balance?
No, sir.
Any other issue for material balance? Anybody else?
No, sir.
Everybody is comfortable with material balance? Long time ago we have done. Now we need to find the outlet temperature. Okay, so let's do that. Now reactions are happening. So let us take a reference as 25 degrees centigrade, 1 atmosphere absolute pressure, like we have been doing, because reactions are occurring, because the heats of reactions are given at 25 degrees centigrade. Standard heats of reaction are given. Remember, this delta H 0 means the standard heat of reaction. For the first reaction, it is minus 25 kilocalories per gram mole. Again, just to repeat, just to make sure everybody is comfortable, the minus sign, this minus sign is going to indicate that it is an exothermic reaction. Exothermic reaction means heat is generated when the reaction happens, and if I am maintaining adiabatic conditions, the outlet temperature will be higher than inlet temperature. Do you agree with this? It's just like the experiment that you may have done. Add sulfuric acid to water. That's a exothermic reaction, dilution. It is not a reaction per se, but it is a dilution, heat of dilution. It's exothermic, and that's why the temperature rises. The heat is generated. That's why the temperature rises. Final mixture is hotter than the starting mixture, starting two components, water and sulfuric acid. Do you agree with this? Do you agree with these statements? Anybody has any doubts? Anybody has any issues? So even before we do anything, we automatically know that this outlet temperature is going to be higher than 150 degrees centigrade. So if you have made a calculation mistake and you are getting a temperature of less than 150 degrees centigrade, obviously somewhere you have gone wrong in the sign, or somewhere you have gone wrong in the calculations or something like that, right? Do you agree with that? Already we know that this outlet temperature is going to be higher than 150 degrees centigrade. Everybody okay? Not okay? Yes, no?
Yes, sir. Okay.
Okay. So now we try to look at all these enthalpies coming in. So what are we doing? We are saying that 25 degrees centigrade, 1 atmosphere absolute conditions, we can say that all the substances in their natural state, in their state at these conditions, have zero enthalpy. So in this particular case, what are the substances that are involved? Ethylene in the gas state, ethylene oxide in the gas state at 25 degrees centigrade, 1 atmosphere absolute pressure, nitrogen, oxygen, CO2. What else is there? Nitrogen, oxygen, CO2. Water. Water is also there. So we will look at water. We will say in the natural state, water in the liquid state also has zero enthalpy. Right? Do you agree with that? Do you agree with that? Just 1 second. Give me a second. Yeah. Water in the natural state of water at 25 degrees centigrade, 1 atmosphere is the liquid. Do you agree with that? Yes, no? So we
Yes,
are
sir.
saying that these have zero enthalpy. Now, if we give stream names, let's call the inlet stream as stream 1, outlet stream as stream 2. Okay. So the reactor is adiabatic. So what we can write? Enthalpy coming in from stream 1 plus enthalpy generated by way of reactions is equal to enthalpy leaving in stream 2. Do you agree with this enthalpy balance? Do you agree with this enthalpy balance? Anybody agrees? Anybody disagrees? Somebody say something.
Agreed, sir. Agreed.
Agreed. Okay. Okay. So now we have to evaluate enthalpy coming in from stream 1. This stream 1 contains ethylene gas, oxygen gas, nitrogen gas, 25 gram moles, 8 gram moles, and 67 gram moles. and these gases are at a temperature of 150 degrees centigrade. So with respect to this reference, the enthalpy of this stream 1, we write that here, stream 1 would be moles of ethylene into Cp of ethylene into dt plus moles of oxygen into Cp of oxygen into dt plus moles of nitrogen Cp of nitrogen dt. Just to make your life simple, I have given all these Cp's to be the same and ideal gas. So all these Cp's are same, they are equal to 7 calories per gram mole Kelvin. So we can simply take them common. So the enthalpy of stream number 1 would simply be 100, 25 plus 8 plus 67 into 7 calories per gram mole Kelvin multiplied by 150 minus the reference temperature. So 100 into 7 into 25, this is so 100 into 7 into 150 minus 25, that's 125. So this is 87,500. It is calories. So if you want to write in terms of kilocalories, you can write, or if you want to keep it in terms of calories, you can keep in terms of kilocalories. But make sure that this is written, you have written the units properly, that it is in terms of calories, because now heat of reaction is given in terms of kilocalories. Now, one more small issue, one more small thing that we need to take care is look at the heat of reaction for the second reaction. Heat of reaction for the second reaction is minus 315 kilocalories per gram mole of ethylene. Look at the state of water that I have given in the second reaction. What is the state of water that I have given in the second reaction?
Gaseous.
Gaseous, right? So rather than taking this in the liquid state, it's okay if you want to take it in the gaseous state. Okay? Or if you want to keep it in this liquid state, that's a very systematic thing to do. If you want to keep this reference condition as H2O liquid in the zero enthalpy, let us make sure that this reaction also we write with respect to water in the liquid state. So we would have to write C2H4 gas plus 3 oxygen gas, giving you 2 CO2 gas and 2 H2O liquid, and then delta H0 for this reaction we will have to write from this reaction and the latent heat of water vaporization at 25 degrees centigrade. Okay, do you agree with that? If you are taking everything in the standard state, 1 atmosphere, 25 degrees centigrade, and the natural state, then you better take this as H2O liquid. But then you better also write the reaction as H2O liquid, because it is delta H0. So this delta H0 we have written, but it is not accurate delta H0 unless I say that okay, water is not condensing anywhere in this reactor. Water is always there in the gas state in this process. Nowhere the water is going to come into liquid form. So whether I convert this into liquid state and then take this as a liquid state, or whether I take this as a gas state and write the reaction in gas state, it is one and the same thing. Do you agree with that?
Yes, sir.
Right. Then we don't have to worry about latent heat of vaporization of water, because it is just going to get added up to this 315, and it is going to be taken up when we convert this water into the gas, because the enthalpy leaving in stream 2, the stream 2 has water in the gas state. Okay? If you don't agree with me, it is okay just now. Maybe you can solve the problem with water in the liquid state and converting these reactions into the liquid state, or you take water in the gas state and keep the reaction water as in the gas state. Okay? Solve it by two ways, you will get exactly the same answer. Anyway, okay, so let's go forward. So we'll take water in the gas state having zero enthalpy. Okay, it is okay because nowhere water is condensing out in this process. Everywhere water is always in the gas state. All right. Okay, so now enthalpy generated by way of reactions. Enthalpy generated by way of reactions. Look at what we did last time. We looked at temperature versus enthalpy diagram. 25 degrees centigrade, we have our reactants and we are going to convert them into products. These delta H 0, they are known. Okay? Whereas actually in the reactor, they are entering at 150 degrees centigrade and they are going to get heated up to something more than 150. So let's say they get heated up to some T degrees centigrade. So we are going to have our products leaving at T degrees centigrade. This is how it is going to go inside the reactor. Look at last time's lecture. We said that, recall last time's lecture. Recall what we said. Some gram moles react, temperature goes up. Some gram moles react, temperature goes up. Some gram moles react, temperature goes up. So going from, in this particular problem, now we are going from this state to this state. We can go by any way we like. One of the ways we can go is we can go to here. We can do the reaction at 25 degrees centigrade and we can heat up the products from 25 to whatever temperature is there. Or we can say reaction occurs at 150 degrees centigrade and the products get heated up to T degrees centigrade. Or we can say everything gets, all the reactants get heated up to 25, all the reactants get heated up. Let me take another color, maybe this. So reactants get heated up from this to T degrees centigrade and then the reactions happen at T degrees centigrade. Right? So let's just take this red path. It is always easy to think as if the reactions are happening at 150 degrees centigrade. So now we are saying enthalpy generated by way of reactions, and so all we need to do is look at delta H for the, not zero, I should not write zero, it's not a standard state. I would say delta H for the reaction 1 at 200 degrees centigrade I need to find out, and delta H for the reaction 2 I need to find at, sorry, not 200, 150, sorry, 150. That's the temperature, 150. Right? So this heat of reaction is what we need. This heat of reaction for this step, let's call this as A, B, C, D, E, F. Right? We need the heat of reaction for the step A to D. Right? When we work out this, it is exactly this diagram that we are doing. When we say delta H of reaction 1 at 150 degrees centigrade, we say it is same as delta H of reaction at 25 degrees centigrade, 25 degrees centigrade plus integral Cp from 25 degrees centigrade to 150 degrees centigrade, Cp of products minus Cp of reactants into dt, all products and all reactants with their stoichiometry. It is this blue thing, A to B to B to C, C to D. That is what we are doing when we are going from A to D. So automatically, although you are saying you are going by A to D, what you are actually doing by doing all this is you are going from A to B to C to D. Right? So just think about all this. It is just a visualization. It is just it is just how we do accounting. So now this is straightforward. We can find out delta H of reaction at 150 degrees centigrade. We can find out delta H of reaction 2 at 150 degrees centigrade. This also we find, it is straightforward. We have done it last time. We can do it again. Now enthalpy leaving in stream 2. So this would be heat. So total heat generated by way of reaction is equal to heat generated by reaction 1 plus heat generated by reaction 2. In reaction 1, how many gram moles are reacting? 2.125 gram moles are reacting. In reaction 2, 0.375 gram moles are reacting. So heat of reaction in heat generated by way of reaction 1 is going to be 2.125 multiplied by delta H of reaction 1 at 150 degrees centigrade. Remember, this delta H for reaction 1 is going to be minus something, right? Suppose it is how much? At 25 degrees centigrade, it is minus 25, right? So suppose if we find this out, just assume right now that delta H for reaction 1 is, let's say, minus 28 kilocalories per gram mole, and for reaction 2 it is minus 310 kilocalories per gram mole. Just assume right now. Assume. You can actually calculate, but if you assume right now. So now this minus sign is going to just indicate that heat is generated. So I don't need to take that minus sign when I'm calculating the heat generated. Right? So it is just 2.125 multiplied by 28. This is in terms of kilocalories. And for the second reaction, 0.375 multiplied by 310. It is generated in terms of kilocalories. All right. Or if you like, you can say, it is minus delta H. So minus delta H, minus will take care of this minus sign. Either way you like, or you want to just logically think that it is minus is heat is generated. So just multiply by the absolute magnitude, modulus of that minus 28, because it is already we are writing as generated. So this is in terms of kilocalories. So take care of units. Whereas this is in terms of calories, heat generated by enthalpy coming in from stream 1. Okay. Now enthalpy leaving in stream 2, right? This is at T degrees centigrade. So from 25, that's my reference, to T degrees centigrade, it is number of moles of number of moles of ethylene into Cp of ethylene. And because all Cp's I have given the same, so number of moles of ethylene plus number of moles of ethylene oxide plus number of moles of oxygen plus number of moles of nitrogen plus number of moles of CO2 plus number of moles of water in the vapor state into Cp of ideal gas. So that is just 7 into dt. And because it is just Cp is independent of temperature, this integration also I don't need to do. It is just T minus 25, right? So all this you can find out. Again, this is going to be in terms of calories. So this will be some unknown. It will be some function of temperature. It's an algebraic equation. So all I have to do is this 87,500 calories plus this 2.125 into 28 plus 0.375 375 into 310. This is in terms of kilocalories, must be equal to all this going out in terms of temperature T, some function of temperature T. It's a linear algebraic function in terms of calories. Right? So take care of the units. It is in terms of calories, this is in terms of kilocalories, and this is also in terms of calories. So either you can convert this to calories by multiplying by 1000, or convert the calories into kilocalories. Any way you want to do it is okay. So temperature you will get in degrees centigrade. All right. Is that okay? Anybody has any doubts? Anybody has any issues? Anybody has any issues? Can we go forward? Can we go to the second part of the problem?
Yes, sir.
Can we go to the second part of the problem? Yes, no.
Yes, sir.
Yes, sir. Yes, sir.
Let's go to the second part of the problem. Now it's an isothermal reactor. Right, material balance remains the same. Still have 10% conversion. We still have 85% selectivity. So C2H4, oxygen, nitrogen, 25, 8, 67. These many gram moles come in at 150 degrees centigrade. Unreacted ethylene, ethylene oxide, unreacted oxygen, nitrogen inert, CO2, water, water, all these gram moles. These we already know, everything we know. And because it is isothermal, temperature will be 150 degrees centigrade. Okay. Now, because it's an exothermic reaction, the temperature will rise. And because I want to maintain isothermal conditions, I have to take out heat. I have to remove heat from the reactor. Okay, so the way we remove heat from the reactor is we have a jacket on the outside of the reactor. So this reactor is going to be like a tube. Imagine a tube. And the catalyst that is there for this reaction. Anybody knows the catalyst for ethylene to ethylene oxide? No?
No, sir.
Oh, okay. It is silver catalyst. So it's a silver impregnated in alumina. So the jacket is going to be there. Imagine another tube. So if you look at this as an elevation, if you look at the end elevation or side view, I don't know what you call in engineering graphics, end view or side view or what, end elevation, what do you call? Engineering graphics.
So, like, sectional view, is that?
You call it as side view or end elevation? What do you call?
So we haven't done elevation.
So we
Like
call it
engineering
just
graphics,
elevation.
Just tell you look at it from this side. You look at it from this side. Array, if you have a isometric, right, L, B, H, if you look at it plan, so plan means view from the top, it will look like a rectangle, L into B, this is your plan. If you look at it as elevation, it will be another rectangle, but L and H. If you look at side view or end elevation, it will be another rectangle, B into H. ये सब किया नहीं किया है?
Yes,
Engineering
sir.
graphics, huh?
Yes, sir. We have done.
हाँ. So that's what I'm asking. Elevation plan ये सब किया है ना? ये सब क्यों करते हैं? So that we can visualize. So if you look at this reactor from the side view or end elevation, it will look like this one tube. This is packed with the catalyst, and jacket is going to look like another tube. Okay. So I supply water, saturated water at high temperature pressure, and I get steam, saturated steam at high temperature and pressure, same temperature and pressure. And if you imagine that your reactants are entering this inside tube at the center, they are entering through this inside tube, they are going into the plane of the screen and coming out from the other side of the screen. Can you visualize? If you want to draw isometric, this is your draw figure. This is your inside tube. It is full of catalyst. Reactants are entering, and products are leaving at 150 degrees centigrade. Everywhere surrounding this is another tube. Obviously now these should all be dotted lines, but that's okay. And this outside tube has liquid water entering and steam going out. Everybody can visualize? Yes, no? Yes or no?
Yes, sir.
All right. Anyway, that was just a way to visualize. All right. It does not change our solution in any way. It is just for, I was just explaining just to help you to visualize. Saturated water enters and saturated steam goes out. And we are saying that saturated water enters at what temperature it was entering? 130 degrees centigrade. 30 degrees centigrade. Saturated steam goes out at 130 degrees centigrade. Right? So let's give some stream numbers. Let's call this as stream number 1. Let's call this as stream number 2. Let's call this as stream number 3. Let's call this as stream number 4. Now what enthalpy balance would we write? Enthalpy coming in from stream 1 plus stream 2 plus enthalpy generated by reactions. Now the reactions are happening at 150 degrees centigrade. There is no doubt about it because it is isothermal. Everywhere inside temperature is 150 degrees centigrade. That's how we are removing the heat. Must be equal to enthalpy going out in stream 3 and stream 4. Do you agree with this enthalpy balance? Yes, no?
Yes, sir.
Okay.
Yes, sir.
Okay. So let us just look at stream 1. Again, our reference is 25 degrees centigrade, same reference we are taking. And stream 1, we have already got the enthalpy. Right? So this stream 1, we already know the enthalpy. Stream 3, we already know the enthalpy going out. Right? Oh, sorry, we don't know. It is at 150 degrees centigrade. Earlier it was at T degrees centigrade, but it is very straightforward to evaluate the enthalpy of stream 3 at 150 degrees centigrade with respect to our reference. Stream number 2, now this enthalpy you can take, it is saturated water at 130 degrees centigrade, so you take it from steam tables. You want me to put up the steam tables, or will you be comfortable looking at the steam tables?
Sir, can you once tell?
Okay. Okay, let me open that steam table. Have you downloaded steam tables for yourself?
Yes,
Yes,
sir.
no?
Yes, sir.
Yes, yes. Okay, so
Yes, sir.
maybe you already know how to look at it. Okay, fine, fine. Maybe already you are comfortable looking at them, but let me just once again, for the last time, let me just show them. Let me start sharing. Stop. Stop this. Okay, now I want to start. Once again, my computer is a little slow. Okay, now you are able to see the steam tables. Are you able to see? Yes or no?
Yes, sir.
Right.
Yes, sir.
Right. So we want to look at the saturated temperature table, and we want to look at 130 degrees centigrade. So this is 130 degrees centigrade is here, right? 130 degrees centigrade is here. So this row we want to look at. This row we want to look at. Okay. So enthalpy of the fluid HF, that is the enthalpy of liquid saturated water, that is 546.058, and enthalpy of the gas Hg, it is 2719. HFG is the change of enthalpy in going from liquid to gas, that is 2173.8. Right, let's write that 546.058. So stream 2 enthalpy is 546.058. 546.058. It is kilojoules per kg. Look at the units. And stream 4 enthalpy is, let's look at the steam table, is 2719.86. 2719.86 kilojoules per kg. Look at the units. It is kilojoules per kg. Kilojoules per kg. Okay, comfortable in looking at the steam tables?
Yes, sir.
Okay, let me stop. Let me go back. Okay. Right, so I have written these here. Enthalpy of stream 2, enthalpy of stream 4. This is per kg. We want to know how many kgs of steam are generated. So we will say, let's say x kgs of saturated water enter, x kgs of saturated steam we will get. Right. So enthalpy generated by way of reactions we have already worked out. Take care of units. Enthalpy of stream 1 that we got was in calories. Enthalpies of stream 2 and stream 4 was in kilojoules per kg. Enthalpy of stream 3 we got in terms of calories, because R we took in terms of calories. Enthalpy generated by way of reactions we got in terms of kilocalories. Right, so convert everything into one set of units. If you want to stick to kilocalories, that is fine. If you want to stick to calories, that is also fine. But essentially solve for X. Do you agree? Yes, no?
Yes, sir.
Yes, sir.
Okay, can we go to the next problem? Anybody has any doubts? Can we go to the next problem?
Yes, sir.
Yes, sir.
Again, it's an extension of the same problem, just to let you know how differently we can do things. But look at this problem. Okay, I will explain this next problem. Yeah, it is a continuation of this problem, or another way of doing this problem. So we said that this same ethylene oxide reactor, if I operate it in an adiabatic mode, this temperature is going to be 396, 398. Let's not worry about whether it is 396 or 398. Let's say around 400 degrees centigrade. Now, how am I going to get this up to 150 degrees centigrade? I have ethylene, I have oxygen, I have nitrogen. This is going to come from air. So that means these things are going to be available at around 30 degrees centigrade. Isn't it? Maybe room temperature that day, or maybe ambient temperature that day was 35. Maybe ambient temperature that day was 21. Maybe this plant is in Canada, where temperature nowadays is 45 degrees centigrade. Or let's say this plant is in South Africa, where temperature these days is 10 degrees centigrade. Anybody looks at weather reports, or they don't look at weather reports? All right, jokes apart. So these are going to be available at 30 degrees centigrade. That means if I want the reactor to be supplied at 150 degrees centigrade, I need to heat it up, right? I need to have a heater that will heat up the gases, and then these heated up gases will go at 150 degrees centigrade. Similarly, this 400 degrees centigrade contains this ethylene oxide. Now we want to recover this ethylene oxide, so we are going to cool this gas, right? So we are going to cool, and then we are going to take out this gas maybe at 50 degrees centigrade, so that we can recover ethylene oxide from it. So do you see that we have to heat somewhere, we have to cool somewhere, if I maintain the reactor adiabatic. Even if I have an isothermal reactor, by having a jacket, I still have to supply heat. I still have to cool the outgoing gas, but not obviously not from 400 now. It will be cooled from 150 degrees centigrade to 50 degrees centigrade. And I have to additionally take out heat. I have to cool the reactor by converting liquid water into steam. Right? Do you agree with that? How many extra things we are doing? We are heating something, we are cooling something, we are in addition taking out heat. Can you think of one way of doing all these things? Can you think of a different way of doing these things? Can you think of doing the heating step and the cooling step in a different way?
So can we use the steam for heating the mixture, the
Yes. Okay.
C2,
Okay.
O2 and 2?
Right. Okay. So heater. What temperature this steam is available at?
130 degrees Celsius.
130 degrees centigrade. If I use this steam as a heating medium and get back the water, which I can recycle back to this process, will I be able to heat it up to 150 degrees centigrade?
No, sir.
No. Why not?
So because the temperature difference is 100 degrees Celsius only.
Temperature difference is 100. 100 किधर है?
So steam is at 130 and the air is at 30 degrees Celsius.
At what temperature we want this gas to come out at?
150.
So we wanted at 150 and the steam would be at 130.
130. So there is no way I can heat it up this to 150 degrees centigrade. Right? Do you agree with that?
Yes, sir.
Okay. So this is, yes, it's a possible way, good way that we have thought of.
Sir, would a step-by-step heating work?
Step by step means,
So as in we raise it to a certain temperature before it
okay,
enters the reactor.
okay. So we raise it up to, so if we use this steam which is at 130 degrees centigrade, maybe we will heat it up to 110 degrees centigrade. Okay, now,
And then when the products come out,
uh,
we
yes, yes, you are on the right track.
we use that heat also to heat the reactants before.
Right,
So it
right, right. So can we do like this? We operate adiabatic reactor, but we don't heat the reactants, we don't cool the products. This gas we supply to heat exchanger. So shell and tube heat exchanger, if you like, means shell and tube exchanger means. Oh, let me show you a picture of shell and tube exchanger, uh, just so that you are comfortable with visualizing. One second. One second. Why it's not copying? Right. Continue sharing. Right. So this is how a shell and tube exchanger is going to look like. There are these tubes, and there is an outside shell. So this tube side, I may supply my feed gas. So feed gas 150 degrees centigrade will come in. It will go through these tubes, and it will come out from this outlet. Another gas I can supply on the shell side. So if I look at it from end elevation, if I look at it from this side, it will look like this. It will look like a outside shell, and inside there will be tubes. These are all tubes which are going from one end to another end, and the feed gas that we have supplied is going to go through all these tubes, and the shell side gas is going to go all around the tubes and come out from the other end. Okay, you can visualize? Yes or no?
of so the conductivity of the shell or the tube should be very less, right? So that
Conductivity should be
maximum heat.
high, no? Then heat transfer will happen
Oh,
very
yeah,
nicely.
high, high.
Uh, yes, yes. Conductivity should be high. This is another nice picture. It shows a 3D kind of a view. Right. Are you able to see? So this, you see these are the tubes. This is the shell, outside shell, isometric kind of a view. These are all tubes you can see. So the shell side, the tube side gas comes in. It goes through these top set of tubes, goes through these bends, and comes out from this end through this outlet. And the shell side comes here, goes in as this zigzag manner, and comes out outside. Right. So these are called as shell and tube exchangers. So you can just do Google, you will be able to see so many pictures of shell and tube exchangers. Anyway, let's not worry too much about these shell and tube exchangers right now. In semester 5, we will do all these things in a lot greater detail. We will be able to design shell and tube exchangers ourselves. So let's say on the tube side, I'm just depicting the tubes like this, squiggly lines, and the shell side fluid is going to come from one end and it is going to go out from the other end. So I will take this hot gas. So this is at 150 degrees centigrade. I will take this hot gas I will pass it through the shell side, and this hot gas will come out. Let me try to confuse. Let me draw it here. Right. So this hot product gas is going to come into the shell side of the exchanger, and then that will get cooled. And as it gets cooled, it is going to heat up my feed gas as well. Do you agree with that? Yes, no?
Yes, sir.
Yes.
Yes, sir.
Okay. All right. So okay, so let's say we are operating this adiabatically. So obviously this temperature is going to be higher. It's going to be 396 degrees centigrade. Okay. And then this is going to get cooled. If this is, let's say, 30 degrees centigrade, can you tell me what this outlet temperature would be? Then we'll talk about it. Obviously now reactor material energy balance you don't have to do, it's already done for you. It is 396 or 398, whatever you want, it doesn't make any difference. If you want to take 400, you take 400. Now only we are going to look at this exchanger. I have gas coming in at 30 degrees centigrade, gas going out at 150 degrees centigrade. Product gas is coming in at 400 degrees centigrade. I would like you to calculate temperature of this outgoing gas. Okay, then we will talk about it. Let's assume that Cp is all the same. It's like an ideal gas. Cp is 7 calories per gram mole Kelvin. So these kinds of heat exchangers, they are called as feed product exchangers. It is exchanging heat between feed and the product. And this is one very common way of doing things in a plant. So you don't have to use any additional heating medium, any additional cooling medium. It's a very, very common thing to do in chemical plants. Obviously, it's a continuous process. Otherwise, I would have to store this gas. Storing a gas is not possible. It's a continuous process operating at steady state. Calculate this temperature of the outgoing gas. Outgoing product gas. This should take less than few minutes to do. What is to be calculated is clear to everybody.
Yes, sir.
Yes, sir.
There's an important point that I want to make. That's why we are doing this problem. One is, yes, of course, it is a very common way of doing things.
Sir, is there any phase change?
Is there any
Phase change?
phase change? Which phase change?
Like here, H2O may liquefy or anything.
Then you find out now what temperature it cools to and check if it is below the dew point. If it is below the dew point, water will condense. If it is not below the dew point, it will not condense. Praveen, is that okay?
Yes, sir.
I mean, why do you ask me? Whether I say yes or no has no connection. I may say no, there is no phase change, but if temperature is below the dew point, phase change will occur whether I like or whether I don't like.
Okay, sir.
The point that I am trying to make is that you should be able to decide these things yourself, not have to rely on somebody to tell you whether phase change will occur or not occur. Do you agree, Praveen?
Yes, sir.
So assume phase change doesn't occur, calculate the temperature, check if it is below the dew point or above the dew point. If it is below the dew point, then yes, phase change will occur, then you have to account for that. So obviously your calculation has to be redone. So you will have not just the gas, but you will also have liquid water. Okay, Praveen?
Yes, sir.
What takes so long?
Sir, 279 degrees Celsius.
Okay. Ishan.
Sir, same sir.
Yes, sir.
279.
278.
Yes, sir.
I
Even
mean
I got that
79.
answer.
Oh, I should not violate material balance. The number of answers cannot be more than number of attending people. I can't read people's minds which are not there. Okay, you need more time or everybody is okay? We can call it a stream 1, stream 2, stream 3, stream 4. Enthalpy balance we can write enthalpy in from stream 1 and stream 3 must be equal to enthalpy going out in stream 2 and stream 4. Do you need more time or we can go ahead? Anybody needs more time or can we go ahead? It's very straightforward problem. What is taking so long?
Sir, same answer.
Okay.
Yes, sir.
Right. So the point that I'm trying to make is this. Anyway, this will all be there in semester 5. Uh, I'm just telling you what things are going to come. So we can operate this exchanger in two ways. Something we call as co-current, meaning both the cold fluid and hot fluid flow in the same direction, left to right in this particular case, or it could be right to left. And if you plot temperature with respect to A and B, the temperature of the cold fluid will increase, temperature of the hot fluid will decrease, right? But you see, temperature of the hot fluid has to be always greater than cold fluid, only then it will act like a heating medium. So heat is getting transferred from this hot fluid to cold fluid. That is why the hot fluid temperature is falling, cold fluid temperature is increasing. Or we can operate in a counter current manner. We can operate in a counter current manner, meaning hot fluid goes in one direction, let's say left to right in this particular case, and the cold fluid goes from right to left in this particular case. So if you plot temperatures between this A and B, the hot fluid comes in at a high temperature, goes out at a lower temperature. The cold fluid comes in at a lower temperature, gets heated up. Again, heat is being transferred. So if you want to maintain a 20-degree difference, you have to maintain a 20-degree difference between the hot fluid outlet temperature and the cold fluid outlet temperature if it's a co-current exchanger. But if it's a counter current exchanger, you have to maintain 20-degree difference between the hot fluid inlet and cold fluid outlet, or the hot fluid outlet and the cold fluid inlet. Can you tell me which one is better, co-current or counter current? Which case?
Excuse me, sir.
Yes, Hardik.
Please could you explain it again, sir?
Okay. There are two ways in which we can operate this exchanger. Hardik, are you listening?
Yes, sir.
There are two ways in which we can operate this exchanger. One called as co-current manner, other called as counter current manner. Look at the co-current picture. Look at this picture.
Yes,
Co,
sir.
co means they are flowing in the same direction from left to right. Do you agree?
Yes, sir.
Now co-current, if you plot temperature on y-axis versus distance between A and B, or versus length from A to B, this maybe is at 30 degrees, 400 degrees centigrade. This is maybe at 30 degrees centigrade. Cold fluid inlet. What is the cold fluid inlet? Is a reactant gas. And what is the hot fluid? Is a product gas. Do you agree? As they go along this exchanger, heat is being transferred from outside the tube to inside the tube, and the reactant gas gets heated from 30 degrees centigrade to higher temperature, let's say 150 degrees centigrade. Okay. The cold fluid gets heated from 30 degrees centigrade to 150 degrees centigrade for this particular application. The hot gas, 400 degrees centigrade, let's say it gets cooled down to, what temperature was there? What was the temperature? 279. Let's say 280 degrees centigrade. The gas gets cooled up to 280 degrees centigrade. So this is 280 degrees centigrade. And this is 150 degrees centigrade. Do you agree, Hardik?
Yes, sir.
Do we have a 20 degree difference, at least 20 degree difference everywhere?
Yes, sir.
Right? But now you look at it in a counter current manner. Counter current, meaning they are flowing in the opposite directions. Hot fluid is going from left to right. Cold fluid is going from right to left. Now if you plot temperature on the y-axis versus length between A and B, between A and B, now tell me which temperature is 30, which temperature is 400, and which temperature is 150.
Sir, TC will be the lower temperature and TK will be the higher temperature.
TC, there is TC in and TC out, which is 30 degrees centigrade.
TC in.
Right. This is 30 degrees centigrade. This is 150 degrees centigrade. This TH in is 400 degrees centigrade. TH out is our 280 degrees centigrade. All right. Do you agree?
Yes, sir.
Now, if I had wanted, I could have allowed this temperature to go to 380 degrees centigrade, and I could have cooled this down to 50 degrees centigrade, maintaining 20 degree difference. Do you agree? Do you agree with this?
Yes, sir.
If I had wanted, I could have heated the cold from 30 degrees centigrade to 380 degrees centigrade, and the hot fluid I could have cooled from 400 degrees centigrade to 50 degrees centigrade. Do you agree with that in a counter current manner?
Yes, sir.
Is it possible in a co-current manner?
No, sir.
No. So maybe I would have got this heated up to maybe 210 degrees centigrade. Maybe this would have cooled up to 30 degrees centigrade. Do you see that? Because I wanted a 20 degree difference. I'm just saying 210 to 30. It may not be 210 to 30. It may be something else. It may be 200 and 230 or whatever, or 205 and 225. And do you agree with that?
Yes, sir.
I can get better heat recovery in a counter current exchanger rather than a co-current exchanger. So now, which one is better for us,
Counter current, sir.
right? Do you agree, Hardik?
Yes, sir. Thank you, sir.
No issue. This is a very, very important concept of co-current versus counter current. We are going to encounter this concept again and again and again and again and again in second year, third year, fourth year, and counter current is always going to be better. And fifth year and sixth year and seventh year and 10th year and 12th year and 15th year and 20th year and 100th year and 200th year. It's a very, very important chemical engineering concept that we do something in a counter current manner versus co-current manner. There are other things that we do in a counter current manner as against co-current manner, but that we will see as we go along. Let's not worry about that just now. Okay, you want a break of 5 minutes? Then we can go to the next problem.
Okay, sir.
Okay, sir.
Okay, so break of 5 minutes. We'll assemble at 9:50, 50. Okay, shall we begin? Shall we begin?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so next couple of problems that we are going to do. See, we have always been trying to heat up something or trying to cool something, or we have used energy somewhere, right? Electrical energy. We have heated something. We have uh, used some kind of heating source, some kind of cooling source, some kind of cooling device to cool something. Um, so next couple of problems, what we are going to look at is what is the cost of heating something, and what is the environmental impact of heating something. Environmental impact meaning how much CO2 is generated, heating or cooling. And do you remember we did some heating cooling calculations when we were making evaporators, when we were making salt, evaporated seawater to give you the salt. Do you remember this? Yes, no?
Yes, sir.
I gave you some kind of cost for steam that time. I gave you a steam cost of ₹1 per kilogram. Do you remember that?
Yes, sir.
So this is what we are going to do, where this ₹1 comes from. Okay. So what is the cost of steam? We are going to worry about what is the cost of steam. And electricity cost also I told you, right? Electricity that we use in our day-to-day lives. What is the cost of that electricity? What is the cost of your electric bill? Remember we were talking about electrolysis. Somebody was, I think Arya was saying that we should generate hydrogen by electrolysis, and we talked about cost of hydrogen. Do you remember all that, or you don't remember all that?
Yes, sir.
So what cost did we take at that point of time? 1 unit. What is your electricity bill? How many units of electricity do you consume, and how much bill do you get at home?
1 unit is approximately ₹8. That is what we
Yeah.
assumed that time.
Right. So ₹8 per unit, and we are saying cost of steam is ₹1 per kg. So what we want to talk about now is how do you get these numbers? Whether this ₹8 that government is charging, whether it is reasonable, or whether government is overcharging us, or whether government is actually incurring a cost of more than ₹8 and they are giving a subsidy by giving us electricity at ₹8. Right? Second thing we want to look at is what is the environmental impact, meaning how much CO2 is generated when I use 1 kg of steam. How much CO2 is generated when I use 1 unit of electricity. And then same thing we can extend to cost of cooling also. If I have to cool something, how much cost am I going to incur? What is going to be the environmental impact of doing that cooling? How much CO2 is going to be generated by way of that much amount of cooling that we do? So environmental impact, we can think in terms of the CO2 footprint. We can think in terms of the water footprint. Water is a scarce resource. I need to save water because it is useful for drinking, agriculture. So many of our survival depends on water. So what is how much water am I going to use when I use 1 kg of steam, or how much water do I use up when I use when I use 1 unit of electricity? So these are the next couple of problems. These are the things that we are going to look at. How do I get a cost? How do I get a environmental impact in terms of the footprint of the human activity of steam, human activity of electricity on the environment, right? So these are only some case studies. These are only some problems that we are going to do, but you should more look at the philosophy that how do I assess the cost, how do I assess the environmental impact of any activity that we are doing. Right? So let's look at the steam first. Okay, so how do I generate steam? I need to have a heating medium, so I need to have a heat source. So maybe there is a heat exchanger. I will supply saturated water at 130 degrees centigrade, high temperature and high pressure, and I will get some kind of saturated steam coming out of it at 130 degrees centigrade. Right? I would put this inside a coil if you want. So I need a heating source. Do you agree? That will convert this water into saturated water into saturated steam. Do you agree with that? In the previous problem, the heat source was the reaction that was occurring. Do you agree with that?
Yes, sir.
But let's say now our plant is not making ethylene oxide. Then how do I generate this steam? How do I generate 1 kg of steam? Can you think about what could be a heating source? What would provide
Coal.
heat? Huh?
Coal.
Coal. Yeah. So I burn coal and I generate heat, right? Is that what you are trying to say?
Yes, sir.
Okay. But instead of coal, now you remember we did one more problem. We did one more problem when we were talking about calorific value. Do you remember this problem? Do you remember this problem? We talked about
Yes.
calorific value of fuel. We talked about methane as a fuel. We talked about petrol, octane as a fuel. We can also talk about coal as a fuel. Right? Just by looking at methane and octane, can you tell something about the hydrogen to carbon ratio in the fuel and environmental impact, or CO2 footprint if you like? Hardik,
Yes, sir.
just by looking at the H to C ratio in the fuel, can you tell us something about the CO2 footprint?
Yes, sir. 1 minute.
Look at this problem. I put it up on the screen. We use methane as a fuel. We use octane as a fuel. For 1 unit of energy, I generated 0.055 grams of carbon dioxide. In other case, I generated 0.075 grams of carbon. I don't know which ones are right. I think these answers
The
are
circled one. The circled one.
0.069, 0.069, Circled ones were right. Okay. Fine.
Sir, the less the C to H ratio, the
Right.
less carbon dioxide will be emitted.
Correct. Or higher C to H ratio, higher H to C ratio, less is the CO2 footprint. Hardik, do you agree with this statement?
Yes, sir.
C to H ratio.
So,
Lower.
but then the cost factor will be affected, right?
Right. So now, what I suggest you can do is you take coal as a fuel. It's good point, Hardik. You are saying you take coal as a fuel. I'm going to give you some numbers for coal, right? So coal, if you say it contains, let's just say it contains carbon, hydrogen, and oxygen. Let's say carbon is 70%, hydrogen is 5% by weight, and oxygen is the remaining 75, so 25% by weight. C as in H as in element, O as in element is 25% by weight. And calorific value, so lower calorific value is, let's say, 5000 kilocalories per kg. We are not even worried about whether this coal is wet or not, whether it contains sulfur or not, whether it is going to contain ash or not. We are only going to look at the combustion calorific value is 5000 kilocalories per kg. Okay. Can you work out the CO2 footprint? Can you work out the cost? Okay. Not now, Hardik, later on.
Okay, sir.
Okay. In general, can we make this conclusion that higher H to C ratio, I will have less footprint because higher H by C will have higher calorific value. Calorific value. Heat of reaction is one thing, but calorific value in terms of per kg of fuel burnt. So find out, do Google, find out calorific value of different fuels and check what is the connection between H by C ratio and the calorific value. All I'm trying to say is you can find out answers to yourself, answers for yourself. So we need a heating source. So now, Hardik, tell me a bit better heating source than coal. Hardik, are you there? No? Hardik is not there. Anybody there? Nobody is around.
Yes, sir.
Yes, sir.
So tell me a better heating source which will have lesser footprint.
Methane.
Methane,
Methane, sir.
right? Or any place which has more H to C ratio. Better is still hydrogen, no carbon dioxide footprint. Pure H2 gas. But H2 gas I have to generate from somewhere, right? So let's not use that. Let's use the available methane. So I have methane. So let's say CH4. I take air. I burn. So we call this as a furnace where we burn. So this is our flame. Okay. So when I burn methane and air, let's say air we have is 20% excess air. What is going to be this flame temperature? Can you tell me the flame temperature? What do you think would be the flame temperature? Very high. That's why that flame appears as blue, red, green, yellow. Yes or no? Somebody say something. Is everybody clear what I'm asking? Suppose I take methane 25 degrees centigrade. Suppose I burn with excess air, which is also at 25 degrees centigrade. Let me make life simple for you. Let me say it is dry air. If I burn at 25 degrees centigrade, I get a flame. Do you agree that there will be a flame?
Yes, sir.
Yes,
Yes.
sir.
Yes, sir.
The flame temperature, will it be more than 25 or less than 25?
More than 20.
Definitely more.
Definitely. If anybody disagrees with me, they can go to in the kitchen. They can light the gas or light whatever is the fuel, CN, LPG or CN pipe natural gas, whichever one, and try to go near the flame. Don't touch the flame. Okay? Your parents will file a case on me, but don't touch the flame and go near the flame. It's going to be hot, right? Why is it hot?
Giving out heat.
Heat of combustion.
Combustion. The heat of combustion is going to heat up the product gases to a high temperature, and that's what we see as a flame. Do you agree with that?
Yes, sir.
Yes, sir.
Okay. So we can break down this furnace or boiler into two parts. One part like this here. This is one part where combustion is taking place. Or where I should say where flame is present. So what I get is a hot gas going out of this flame, okay? And then this hot gas is my heating source that heats up that supplies the heat to this coil, which contains this saturated water. It is supplied with saturated water. It gets converted into this saturated steam, and this hot gas will now cool, and then I can exhaust that gas. Let's say this gas that I exhaust is at 200 degrees centigrade. Okay? So I can break down this problem into two parts. One part is where the flame is occurring, and the other part 2, where heat is transferred from hot gas to generate steam, and the gas will cool down to, let's say, 200 degrees centigrade. Just some number. Let's not worry about whether it is 200 or 300 or 250 or 290 or 210 or 198. Let's not worry about that. I'm just saying that it is cooled down to 200 degrees centigrade. Do you agree with that? Yes, no? Is everybody able to visualize?
No, sir.
Yes, sir.
Nobody is able to visualize, or nobody is listening, or nobody wants to know anything.
So
So I'm not able to
a little help
visualize.
more if for visualization.
Little bit.
Yes.
So I'll need a little more help for visualization.
Oh, okay, so imagine that you have a burner at home. So you have a PNG at home, and you have air coming in. So there is a burner at your home, gas at home. There is a flame, and then you keep your vessel with Maggi on it and water. Right? Isn't it not consisting of two parts? One part where the flame is generated, and second part where the heating actually happens, but that heating is happening because of the hot gas coming from the flame. Flame is nothing but a hot gas at high temperature, right? That's why we see it. It is appearing to us because it is at a high temperature. It is emitting energy in the visible range. Therefore, it appears as a flame to us. Do you agree with that?
Yes, yes,
Now, are you able to visualize?
yes.
So instead of Maggie, we are going to generate steam by supplying saturated water at 130 degrees centigrade. Okay. So part 1, where flame is present, it is like an instantaneous combustion. And as soon as that methane comes in contact with air, we have provided a spark by way of a lighter, or we have provided an ignition source by putting a burning matchstick to it. It instantaneously burns. Right? We have a fuel, we have air, and we have a source of ignition. Source of ignition is our lighter, or source of ignition is our matchbox, the lighted matchstick. Okay? So this instantaneously it burns. So this region is actually so small that we can think about it as adiabatic. No heat is transferred out of this combustion. Whatever heat of combustion is there, all of that goes in raising the temperature of the gas to a high temperature. So the temperature that we get here, we call it as adiabatic flame temperature. Right? Adiabatic because all the heat of combustion is going in raising or heating the gas to a high temperature, like our sulfur dioxide problem, where or ethylene oxide problem. All the heat of reaction went in heating the gas. Now the reaction is not SO2 going to SO3, it is not ethylene going to ethylene oxide. The reaction now is combustion reaction. So what I want you to find out one is find out the adiabatic flame temperature. Adiabatic because no heat has been lost, no heat has been taken out. And then second is how many kgs of steam will we generate per kg of methane combusted. Okay. So now in the second part, this hot gas, which is at a temperature T, the adiabatic flame temperature, is getting cooled to 200 degrees centigrade, and the heat is getting transferred into raising, converting the water, saturated water, into saturated steam. Now, are you able to visualize?
Yes, sir.
Okay, so you take basis as 1 kg of methane. Just to make your life simple, I am going to give you calorific value of methane. Should I give you a higher calorific value or lower calorific value?
So lower, sir.
Lower,
Why is
sir.
that, Karthik?
Sir, I'm not able to remember, sir. Sir, because the
Why
water
did
conversion
you
is
say
not
lower?
taken into consideration, sir.
Why did
So
you
the
say
water
lower? If
conversion.
you
Sir, temperature is
Ah,
high.
So the temperature is
temperature is
200.
high, correct. Water is not going to condense. So I'm going to look at the lower calorific value. So let me give you that lower calorific value. Where did we talk about these calorific values? Or just do Google lower calorific value of methane. we are going to have 20% dry air. I'm doing you a favor. It is going to contain 20% excess air we are supplying. That is also at 25 degrees centigrade. Water is nowhere condensing. So therefore lower calorific value. All the heat generated is going in increasing the temperature of the gas, the adiabatic flame temperature. And then do the second part, that hot gas at the adiabatic flame temperature is getting cooled. Let's call this as some adiabatic flame temperature. Let's call this as TAD, T adiabatic. That's what I wanted to find out. Now the gas is going to get cooled from the T adiabatic flame temperature to 200 degrees centigrade, and that is going to give heat, convert water into steam. Saturated water at 130 degrees centigrade, it is converting to steam. Saturated steam at 130 degrees centigrade. All right. Can you find out? Is the problem statement okay with everybody? Is everybody clear about what is to be found out?
Yes, sir.
Yes, sir.
Only Ansh is clear about what is to be found out.
Yes, sir.
Yes, sir.
Clear.
Yes, sir.
And Mayur
Yes, sir.
and Om.
Yes, sir.
And Edith. Your voice is so soft, I can barely hear you. Very soft spoken person. Just Google lower calorific value of methane. Will you need the CP values? Do you think you will need the CP values?
Yes, sir.
Yes or no? Do you think you will need CP values?
Yes, sir.
Yes, sir.
Yes, sir.
So where are you going to get CP values from? Do you want to take CP as 7/2R for all gases? Somebody say something. Do you want to take
Okay,
7/2R?
Okay, sir.
Yes, okay, sir.
Do you think it is valid? Do you think this is valid?
No, sir.
No, sir.
No, sir.
Why not?
Sir, because this is the ideal case, right?
It's ideal case, and all these gases, they are going to go to higher temperature. Obviously the flame, the very fact that we are able to see, it is going to emit light in the visible range. If it is going to emit light in the visible range, can you tell me what would be the temperature? There's some law in physics that you talked about, the temperature and wavelength
Yes,
relationship.
sir.
You remember that?
So Wayne's displacement law.
All right. the sun we are able to see yellow because it emits light, because it is at some temperature. Right? Similarly, this flame, if it is bluish flame, it is going to be at some temperature. So obviously this temperature is going to be way high, maybe 1000 degrees centigrade, maybe more than that. So obviously I can't take Cp to be constant. So I have to worry about temperature being increased from 25 to maybe 1000 plus, maybe 1500. So obviously I can't take Cp to be constant, nor can I take it to be ideal, 7/2 R. So what should I do? What should we do if Cp is not equal to 7/2 R and it is not a constant?
So ABC values.
Yeah, Cp is going to be some function of temperature. So look at Himmelblau's book. Look at appendix. So, are you able to see the screen? At Himmelblau's book.
Yes, sir.
Look at all these appendices. Heat capacity equations. Right? You see this? Either it is equation 1 or equation 2. Either it is equation 1 or equation 2. And you can get for different gases. In equation 1 or 2, Cp units are joules per gram mole and temperature is in Kelvin or centigrade. The Kelvin or centigrade is given here, whether it is in terms of centigrade or whether it is in terms of Kelvin, whether it is equation 1 or it is equation 2. So don't expect every data to be given to you. Right, and calorific value, you just do Google. One of the hits you will get is, are you able to see? One of the hits that you will get is this engineering toolbox, which is large data of many things. Are you able to see? Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
So you look at the lower calorific value. So methane is here. It has a higher heating value, it is given, and a lower heating value, calorific value, gross calorific value or net calorific value. So you want to look at this second part where we are talking about this lower heating value. It is given in terms of different units. You can take whatever units you want. It is given in terms of meter cube also, feet cube also, because it's a gaseous fuel. So methane, if you see, net calorific value or lower calorific value is 13.9 kilowatt hours per kg or 50 megajoules per kg. 50 megajoules per kg. Do you agree with that? Higher calorific value, higher heating value is 55.5 megajoules per kg. Are you able to see? Yes, no? Do you
Yes,
agree?
sir.
Do you disagree?
Yes, sir.
So now if I stop sharing this, share the notebook again. So lower calorific value is 50 megajoules per kg. And Cp you can take as a function of A, B, C, D. Right? Shall we stop for the day? You have another class at 10:40, right?
Yes, sir.
You have another class at 10:40, right? Or no class at 10:40? Then we can continue for 5-10 minutes more, or a class is there?
Sir, we have a 10.
You have a class. Okay. So we'll stop. We'll stop now. So do this by Thursday.
Okay, sir. Thank you, sir.
Okay,
Yeah.
sir.
And has anybody looked at